Centrifugal pump, and for today we will discuss about velocity triangle again and the type of blade. So this is the complete velocity triangle, and I hope you already know how to draw this velocity triangle because I have a special notes for how to draw velocity triangle previously. So here we have a blade here, and this blade is for backward blade. So this is an eye, the water come from here. So to draw your velocity triangle, you need to draw first the actual velocity or the absolute velocity, V1 here at this direction. And you draw V2, the actual velocity or the absolute velocity at the outlet at this direction. Then you draw component velocity due to the rotation speed and the blade curve. So we could draw is U1 here, and we draw VR1 here. At the outlet, we could draw VR2 here because this is the shape of the blade at the outlet, and this is U2, the tangential velocity at the outlet. Then we draw a component velocity for the theoretical velocity. So this is the theoretical flow. So we mention as VF1, flow velocity at inlet, and this is the flow velocity at outlet. And flow velocity must be parallel or must at the direction of the radial here. And then because we imagine that V1 is the resultant velocity, so we should have another velocity here. So we call this velocity as world velocity at inlet. So we mark as VW1 here. And the direction is actually from this point to this point, and then continue from this point to this point. So here the V2 velocity is actually from here to here because this component velocity must close loop the actual velocity here or the absolute velocity here. So you must draw V flow 2 here and then continue with V2 here. And then this is the angle. We have two angles mentioned as alpha and beta. So beta 1 is the angle blade at inlet, and beta 2 here is the angle blade at outlet. And alpha 1 is the flow angle at the inlet, and alpha 2 is the flow angle at the outlet. So I repeat about the legend for inlet and outlet. We go first for inlet. So U1 is the tangential velocity, and U1 must be calculated in linear. So if in the question they give you in rotation per minute RPM or in radian per second, so you could change the value by using this equation. U is equal to R omega equal to pi dn over 60. So and then please alert here that if you calculate the value of 1, you need to use all point number 1's value. For example, you want to calculate U1 here, you must use R1 and omega. And please bear in mind that rotational speed, RPM or radian per second, it does not have any RPM1 or RPM2 because the rotation per minute is constant whether you are calculate in inlet or at the outlet. So V1 is called absolute velocity at alpha 1 to tangent. VR1 is the relative velocity to impeller blade. It also can be calculated as V1 minus U1 according to the vector calculation here. So the component velocity for V1 consists of V1 world velocity and VF1 radial flow velocity. So VF1 is the theoretical flow velocity and V1 is the world velocity. It's a turbulent velocity that shifts the actual velocity a little bit compared to the theoretical flow. And beta 1 is the inlet blade angle. This is the legend for the outlet 2. So we have U2 equal R2 omega as the tangential velocity of impeller. We have V2 as the absolute velocity, VR2 as the relative velocity to impeller blade, and for component for V2 can be written as VW2 or wall velocity at outlet, VF2 radial flow velocity at outlet, and beta 2 is the outlet blade angle. So, however, in some textbook, they use another symbol for this velocity triangle. Please don't worry about that because the direction of arrow here is still the same. We have V1 here showing the actual velocity or the absolute velocity, and then you have component of tangential and relative to the blade angle here. And same goes in the outlet here. We have the actual outlet velocity, absolute velocity V2 here, and then this is the velocity relative to the shape of blade here, and this is the tangential velocity at this point. So, and then we have a theoretical here. So, in this textbook, they use Vn1 mean velocity normal at inlet, and this is velocity normal at outlet. And we have a VT here, velocity of turbulence, and we have a VT2 at outlet here. So a slightly different in symbol, but the idea to draw the velocity triangle and the location, the direction of arrow here is still the same. And then I would like to discuss with you about type of blade. We have three type of blade. One is forward blade. The second one is radial, and the third one is backward blade. Please bear in mind that this type of blade is at the outlet, not at the inlet. Means that you need to see how blades was created at the outlet. What is the shape of blade at the outlet? So this is the forward blade. So we have blade here. First thing that you need to know here is the rotation direction. So let's say our rotational direction is counterclockwise like this, means from right to the left. So you just imagine that you are standing at the tip of the blade here and facing at the same direction of the rotational speed. So you will find that this blade is facing forward from you. So we call this blade as the forward blade. So here I would like to show you how to draw a velocity triangle for forward blade. The idea is the same. First, you need to draw the actual velocity at the inlet and the outlet. So we draw V1 here and we draw V2 here. So, and then we draw the component velocity due to the rotational speed. So means we draw V2 from the V1 here, tangential at this point, and then we draw VR1, a relative velocity that parallel with the angle of the blade at the inlet. So we have the absolute velocity, and then we have U1 here and VR1 here. It same goes here when the VR2 mean the relative velocity to the angle at the outlet blade here can be drawn like this. So this angle must be between here VF2 and V2, mean the angle of VR2 must be larger to the angle of V2 here. So we draw the VR2 here relative to the blade angle at the outlet here, and then we continue with the tangential velocity U2 here. So mean this is the resultant velocity, and this is the component of VR2 and U2. Then we draw the flow velocity. So it must be in radial direction. So we draw a straight VF1 here and also VF2 like this. And then why the actual velocity cannot flow like a theoretical velocity here? Because we have turbulence, but I use the symbol of V2 here. So we must connect the VF2 here with V2 here. So at the inlet, we need to draw V1 here and continue with VF1 here. So this is the velocity triangle for the forward blade. This is the velocity triangle for the radial blade. And again, I would like to mention here that the radial blade or the backward or the forward blade is actually the shape of blade at the outlet. So at the outlet here, you will find that the blade is 90 degree. So 90 degree parallel with the radius, and then so we call this type of blade is radial blade. So we could draw a velocity triangle at inlet, same as the forward blade. So we have actual velocity V1 here, and then we have component of U1 and VR1. And then we could draw another component velocity V1 here and VF1 here. So and then for at the outlet here, we must draw first the absolute velocity of V2. So we draw something like this. So we draw an arrow at this direction and we label it as absolute velocity V2. And then we know that the relative velocity, the velocity that flow relative to the angle or relative to the shape of the outlet blade here will become straight like this because the blade is 90 degrees. So the velocity VR2 here will flow 90 degrees too. So we could say that at this point VR2 is actually equal to VF2. And then another component, which is the tangential velocity U2 here, is also equal to the V2. So for the radial blade, at outlet velocity triangle, we only have this kind of triangle. And the value here is VR2 equal VF2 and U2 equal V2 for the tangential velocity. And this is the velocity triangle for the backward blade. As I said, we need to focus at the shape of the blade at the outlet and imagine that you're standing facing to the rotational flow here, rotational direction here, and you will find that the blade is at your backward. So this types of blade is the backward blade. So at the inlet, they will create totally same velocity triangle as what we have previously. So we have the absolute velocity V1 here. We have component of U1 and VR1 like this. And then we have another component of V1 and VF1 like this. At the outlet here, first we need to draw the absolute velocity like this. We draw an arrow here with some inclination and we label as absolute velocity at outlet V2. Then because the angle here or because the blade shape here will create VR2 at this angle, so we need to draw the VR2 parallel with the angle at the outlet blade here. So we draw VR2 like this. Then we continue with the tangential velocity of U2 from this point to the end of V2 here. So this is our VR2 and this is our U2. And then for VF2, VF2 must flow radial at the outlet. So we draw VF2 like this, 90 degree at the tangent line here. So this is VF2 and continue with V2 from this point to the end of V2. So this is the velocity triangle for backward blade.